Namaste, good afternoon and good morning to you all who are in United States and Poland, and good evening to you who are joining from Nepal. This is C.R. Bhatta from West Virginia, United States. I will be hosting today's very special talk. Before introducing our speaker, I would like to make a few announcements. Please be with us. Number one, we will have very interesting talk again on November 22nd for NPA Colloquium Series. Dr. Ved Paudel from Penn State will be talking about thermoelectric technology overview. Please do not forget to join us. Number two, there will be another big event, AWW 2020 NPA Winter Workshop on December 26-27. Please keep following us for the updates. And number three, there will be Python classes for the beginners again, starting on December 19th. Please send us an email if you are interested in that program. And the last one, NPA is launching soon ASTG, NPA Student Travel Grant for our student members. Please stay tuned. Please be informed that some of our programs are especially for members only. So if you are not an NPA member already, please become a member. Just a few clicks through our website, anpaglobal.org. If you are in Nepal or somewhere else and can't be an NPA member but like to join our talk programs, please sign up our signing sheet. And generally, we provide or we post our signing sheets on our NPA Facebook page. You can take from there. And we provide WebEx links to our participants or whoever sign ups for free. Now, without further ado, I would like to introduce today's our very special speaker. Today, we have a very special guest speaker to talk on the topics of Nobel Prize in Physics 2020 from Poland, Dr. Gopal Bhatta. Dr. Bhatta is currently working as a research associate at Astronomical Observatory of Jagiellonian University, Poland since 2013. And very soon he is going to join Institute of Nuclear Physics in Krakow as an associate professor. I would like to congratulate Dr. Bhatta for this, his new endeavor. As many of you know already or might have guessed, his research area is mainly concentrated on multi-frequency variability study of blazars, quasi-periodic oscillations in blazar and binary supermassive black holes, very high energy cosmic rays, and many more similar fields. Dr. Bhatta is an active member of many professional organizations like American Astronomical Society, European Astronomical Society, Polish Astronomical Society, and many more. Dr. Bhatta has authored more than 35 scientific publications in well-known international journals and has become a part of a number of conferences around the globe. Before joining Jagiellonian University, he served as an adjunct faculty at Department of Physics, Florida International University. And regarding his education, Dr. Bhatta did his PhD from Florida International University in 2012 and has completed his habilitation in high energy astrophysics from Jagiellonian University, Poland in 2019. Dr. Bhatta has received multiple awards and media coverage, including mainstream medias in Nepal as well as abroad. So with that, I ask that you give your full attention to Dr. Bhatta and help me in welcoming him to the floor. Dr. Bhatta, microphone is yours.
Okay, thank you for such a nice introduction, CRG. And I would like to also thank Navinji for inviting for this special talk. As you mentioned, today I will be talk about a very special topic, Nobel Prize in Physics 2020, and I'll try to relate my works with the Nobel Prize in Physics, which is mainly on supermassive black holes or black holes, and my similar works. So, as all of you know, the Nobel Prize of 2020 was awarded to mainly black hole theory and observations. So, the award can be kind of divided into two parts. The first part goes to Sir Roger Penrose, for his theoretical work on black hole theory. And the second part is Reinhard Genzel and Andrea Ghez for their observational work on the discovery of supermassive black hole at the center of our own galaxy, Milky Way galaxy. Um, so uh, the black holes are actually not new. They were actually conceived as early as 18th century. But the rigorous formal physical mechanism was proposed by Einstein's general relativity, uh, which is the theory about the mainly about the gravitation. Um, we all know about the gravitation, Newton's theory of gravitation, where uh, two any two objects in the universe attract each other with a gravitational force. Uh, but Einstein came along was and slightly changed the picture. He said that uh, the masses of the objects do not actually uh, exert force on each other the way Newton theorized, but rather uh, the masses curb the space-time, and in that space-time, the other masses respond. So this can be famously paraphrased as space-time tells matter how to curb, and the matter tells how to uh, curb the space-time. So this is John Wheeler's famous statement about general relativity. And as you can see, this is the Einstein's field equations. The left part is mainly about the space-time properties, the curvature of the space properties, and the right hand side is the matter or energy. So basically, what this equation tells that any form of matter or in energy, whether that's via matter or any other forms of energy, it can curb the space time, and then the other masses nearby can follow the dynamics depending upon the curved space times. So that's the paradigm shift perspective of the space-time by Einstein. So in this formal mechanism is built in the concept of black holes. But it is interesting to, or maybe ironical that Einstein himself did not believe in black holes. Uh, Actually, it was the Carl Schwarzschild who first found the solutions of Einstein's equations, and first thought of the uh, spherically symmetric black holes. Uh, but later, uh, but the more robust proof of the black hole came from Roger Penrose along with his works with Stephen Hawking and other colleagues, where he showed that uh, once we accept general relativity, then if there's a compact enough mass, then its contraction or the formation of the space-time singularity is actually inevitable. You can't avoid it. So the Sir Penrose provided a robust theoretical grounds for this kind of concept, the black holes. You know how particular these theorists are about the proofs and theorems and proofs. So that was done in 60s and 70s in Roger Penrose, and for which he was awarded Nobel Prize. So as you can see in the picture, I had an opportunity to meet him and have a conversation with him about this kind of things. Now, the other part is the observation part. Well, as I mentioned earlier, the black holes were theorized long before Einstein, even Einstein, so 18th century. And so after Einstein, the idea became more concrete and more formal. People started looking for black hole, but black hole by definition cannot be seen. It's the singularity is the space-time singularity. So in terms of physics, it's a massive um, mass. So it's so which produces so powerful gravity and gravitational field around it that not even light can escape. That means it's basically is invisible. Should be invisible. So the question would be, how would you hunt for this kind of black holes which are not visible? How can we observe them using telescopes or other the instruments? Um, so and then regarding supermassive black holes, the best way to look for the supermassive black hole would be our own Milky Way galaxy. Well, by the 60s and 70s, it was people were convinced that actually every galaxy contains a supermassive black hole at its center. So in that sense, like sun is our star, and the nearest star. Um, if you want to look for a star, it's the sun for us, the nearest one. And then, so if you want to look for the supermassive black hole, the nearest supermassive black hole, then you have to look into the center of our galaxy. But as you can see in this picture, the center of our galaxy or Milky Way is quite obscured in optical wavelengths, so you can't see anything. There's a lot of gas and dust in between us and the center of the galaxy. So and the Rendell and Andrea Ghez, what they did was they used telescope from infrared telescopes, actually not the optical, because from optical you can see, but infrared, which has the ability to penetrate the dust. So they used infrared telescopes, Keck telescope actually, and we're using adaptive optics, which corrects for the any environmental effects, and tracked a couple of stars which are very close to the center of black hole, which is known as the Sagittarius A region. So there are a couple of stars you can see, SO1, SO2, SO5, SO16. So over the years, they tracked the motion of these stars and figure out that actually there's something invisible, which is mass of in the range of 10 to the power of 6, a million times. Actually, I would like to show you the video, uh, 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 a quick video of what they did. So as you can see, these are the stars I was talking about, as SO1, SO2, SO5. So this is the date runs on upper right. So you can see this is the monitoring of these sources over years and years. Sorry, oops. So so as you see that these are the trajectory of these stars in infrared, and as the time passes and as the time passes, they move quickly around a region, which is this says this region. That's the reason there, and so this implies that there's a something massive lying there. So that's how they infer that our center, our galaxy Milky Way has a supermassive black hole, which is a million times, which is mass million times than solar mass. So now a little bit of more black holes. How do the astrophysical black holes form? So black hole, roughly you can divide them into two categories: stellar sized black hole and supermassive black holes. The stellar sized black holes form during the life cycle of the stars. Here I show you the life cycle of the stars, and the so everything starts with a interstellar nebula, a collection of dust and gas, and which slowly contracts over time, and forms a protostar, and which is in course of forming stars, and that further contracts with gravitation, and then becomes a star, small star. So the upper trajectory is for the not so massive star, so it becomes a small star, and after time, and then the fusion of hydrogen to helium begins, and after some time, it runs out of hydrogen, and then the helium, and the fusion of helium begins. So, but after a while, uh, the 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 fusion stops at the core, so it can no longer can sustain the gravitation, so it collapses. But the outer shell expands, and this stage is red giant stage. And after some time, again the core collapses, and the further the shell is ejected away into space, and that's planetary nebula. And what remains is the core. Remains is a small compact object known as white dwarf, which is actually a electron. You can say an electron star. The gravity is so strong that it crushes it to a very a tiny volume, and the outward pressure is actually provided by the electron degeneracy pressure. So it's kind of electron. You can say electron star. So that's the fate of the not so massive stars. But if the star is a massive, like 10 to above than 10, 7, 8, 10 solar mass, then again everything starts with interstellar nebula and becomes protostar, and then becomes a large star. And the large star quickly fuses hydrogen to helium, and then helium to more massive elements. And then after some time it will become a red giant, red supergiant. Actually, if a sun, it will also become a sun will not become a black hole. It will end up something like what is called brown dwarf. But at some time it will also be a red giant. If our sun will become a red giant, then it will expand up to Mars, so very very far away. So it will all expand. It will engulf all the planets like Mercury, Jupiter, Earth, and Mars. So when the stars are massive, they become red supergiant, massive red supergiant, and after some time, the core will collapse and the outer shell will ejected away, and then which is a very violent phenomenon will take place, which is known as supernova. And what core the core remains is still massive enough, and it's a it becomes a neutron star. So in previous case, it was a white dwarf. The outward pressure was against the gravitation was provided by the electron degeneracy pressure. Now in this case, even that is crushed. That even electron degeneracy pressure cannot provide enough outward pressure. Is crushed further and becomes all electrons are sucked into protons to become a neutron star, and now the star is sustained due to the outward pressure of the neutron degeneracy pressures. And the if the star is more even massive, and even this neutron degeneracy pressure cannot sustain the star, and it will collapse for the collapse to infinite density, and it will become a black hole. So that is how the stellar black holes form. But so again, as I told you, there are two kinds of supermassive black holes mostly. The other kind is supermassive black holes, and which how these supermassive black holes form is not very much clear. But the one picture is more popular scenario is the merging galaxies. So over the times, galaxies merge and become super galaxies, and the centers coalesce and becomes more massive and massive. That's how the supermassive black holes form. And as an example, you might know that the uh, the Milky Way and Andromeda galaxy, the our neighbor galaxy, the nearest extra galaxy, and not our own galaxy, is Andromeda, and they will over time, million and million years, they will also collide and become one. And that's so people think that this is how supermassive black hole form in cosmos. So only last year we saw the shadow of the black hole. So in this picture, which everyone is familiar with this picture, which was released last year by Event Horizon Telescope, and this is M87, one of the massive nearby galaxy with supermassive black hole at the center. And then what in this picture what you see is actually the shadow of the black hole, a supermassive black hole, and which is a billion times the solar mass. Now I would like to, before I go to the kind of sources I work on, which are popularly known as blazars, I'll briefly like to tell about the quasars, the Asians, a little bit of history about this kind of sources. So in 50s and 60s, with war, there was war, and there was a immense progress in the radio telescope because of the communication, so there were radio telescopes which were basically dishes and antennas which were cheap, and you could do astronomy, astrophysics with this. So they discovered many very very powerful radio sources, but they could not see the optical counterparts. I mean, they pointed out to the space and they see a very strong emission of radio emission, but when looking through optical telescope, they don't see anything. And then, but later, as there were more evolution of techniques and telescopes, they actually found the optical counterpart of these sources, and but they appear to be a variable star, just another ordinary stars, which was varying. If you look at them, they almost look like stars. But the thing is that when they analyzed the spectra, their spectra was nowhere recognizable. They were very different kind of. So later they realized it was really highly redshifted, meaning that they were very compact. They were not galactic sources. They were not stars. They were extragalactic objects, meaning very, very far away. Actually, very galactic systems, a core of a galaxy. And it was interesting to note that they were highly variable, meaning they were very compact within few hours. Intraday, actually, what they call, within 24 hours. So they concluded that these are very compact extragalactic sources which produce immense energy. And one of such sources was called blazar 3C273. This is a Hubble picture, and actually it has also jets. You can see a thin kind of ray of light. That's actually its jets, and its redshift was estimated to be 0.15, and that would correspond to 25 billion light years away. So that's how these sources were being discovered in the 70s and 80s, and then they were pretty much established and under a large family called active galactic nuclei. So what they are is there's galaxies, and center has a supermassive black hole, and what it is doing is it is accreting a large amount of matter, and the beast black holes are being fed with a large amount of matter, and producing a large output. So it is interesting to know that the biggest black holes in the universe are also brightest. Contrary to its name, black hole, that you can see, actually the biggest black holes are the luminous sources in the universe. So they're and then now it's pretty much established. They have billion solar mass, and they're surrounded by accretion disks, which spans from zero point 0.1 to 1 parsec. 1 parsec is 3.26 light year, and from the center, some of the Asians, mostly for blazars. There's a relativistic jets coming from near black hole, and which extends up to kiloparsec uh, into intergalactic medium. So this is a very interesting sources, very violent sources, very interesting high energy emission phenomenon. So these are the jets actually we detected from radio telescopes and optical telescopes. So this one is the Cygnus A radio jet. You can see that it even spans megaparsec. The center is the host galaxy, and these are the jets coming out from these supermassive black hole systems, and um, s- you know speeding with near speed of light into intergalactic medium. And this one is actually the M87, the picture I was showing you earlier. And this is another Asian called 3C31. Apparently, it is moving into galactic medium with a fast speed. Because of that, the jets appear to be twisted. So these are again very interesting class of sources. Now, because I mostly work on blazars, I would like to tell you what these blazars are. So as I mentioned you that Asians, some of the Asians have jets coming out of the centers. If that jet happens to point out to our direction within 10 degrees to the line of sight to the Earth, then the special the relativistic effects become very prominent. They appear because of the Doppler effects. They become very very bright and very very variable. The time scale changes. It becomes really bright, and something called headlight effect. And these are the dominant sources of radio to gamma ray. So you can see them in any frequency, and these are very interesting sources to analyze. Now, a little bit of I would like to refresh, recall your memory. So this is the entire electromagnetic spectrum. You can see that how small the optical or visible light window is compared to the wide, broad electromagnetic spectrum. Um, so so in the direction of increasing energy or the increasing wavelength, if the wavelength increases, the photon of or the electromagnetic wave become less and less powerful, and a long wavelength. And if the energy increases, the photon becomes very energetic. So if it has energy higher than visible, they become ultraviolet, and then X-rays and gamma rays. Ultimately, gamma rays are the most powerful photons, or the waves, electromagnetic waves. And so lights, because as we study about the sources using the signals, these are actually the lights are the messengers from these astronomical sources, which otherwise are billions of light years far away from us. So multi-frequency study of these sources is the only way we can know about them better. And so in my studies, I use all these kind of telescopes in wide electromagnetic spectrum. For example, this is a Keck telescope, the optical telescope, one of the through which we take data and analyze them. Actually, when I was in Florida International University, this was one of my main work, monitoring the sources in optical telescopes and studying and characterizing their physical properties. And similarly, I also use the NASA Fermilab telescope, which has energy band of 100 MeV to 300 GeV. Uh, this is a quite modern, very sensitive, and very powerful instrument, which has an orbital period of about 1.5 hour. So every 1.5 hour, it scans the whole sky in gamma ray, and we analyze the data and study about these sources in gamma ray. And similarly, the relatively modern X-ray telescope is the New Star telescope within the energy band 3 to 79. I'm sorry, this is not 70, 79 keV, and this is actually has a two eyes, two instruments, and it looks directly into the accretion disk near black hole environment, because that's where the hard X-ray, something called hard X-ray, arise from. And this is one of the most powerful telescopes which I've been using for a long time. And this is a radio telescopes, and they're typically in gigahertz. Uh, this allows us to see the jets and the central radio core systems in supermassive black holes. So using all these telescopes, I have made a number of studies, and which I'm going to talk on briefly. See, one of the things I did was that this, as I mentioned you earlier, the blazar has vary in all time scales, like from few hours to years or decades. They change their flux. So in this plot, what I show you is the x-axis is the time actually, and then y-axis is the flux, normalized, of course. And then what you can see is that even few hours, the flux of one of the blazar called S50716 plus 704 changes so rapidly, so violently, so meaning that this kind of emissions are coming directly near the innermost regions around the massive supermassive black holes. And this was the project I did in 2014, in which what I did was I coordinated a worldwide campaign, in which several astronomers from all around the world participated. So what we did was we tracked a single source for 5 days. From India, from China, and from Europe, from USA. So every part of the Earth, we tracked the single sources, and we were able to produce this wonderful light curve. Some of the gap that you can see, that because we didn't have a telescope in that part of the region, so we can have. So this tells what kind of variability we're talking about. So this was one of my early work, and we published this paper back in 2016. As you can see, there's involvement of a lot of astronomers all around the world, and I was fortunate to coordinate this event and produce wonderful results. And then other things with a couple of my students, I studied a large sample of the blazars using her X-ray new star telescopes, X-ray telescope space telescopes, and then you see that the x-axis times in its top figure is something called kilosecond. So in few hours, you see that the flux changes so rapidly, and this is there, the spectra, and you can see that there's a power law spectra that indicates the non-thermal origin of this kind of emissions, which are again consequences of supermassive black holes. And to the right, you can see something called hardness ratio, and you even can see a loop around, which has a very interesting implications in terms of science and the energetics. And this work was done with some of my students at the time, and then we produced this paper back in 2018. Um, Now, so up to now, I talked about supermassive black holes, but recently there's we are also convinced that there are actually systems of binary supermassive black holes. The binary black holes are galactic sources, so they're pretty common in everywhere. For example, in gravitation wave or gamma ray bursts, and so most of the stellar systems are binary systems, and it is highly likely that one of them source is either neutron star or a black hole, or in some cases both of them can be black hole. So that's a stellar super black holes. But now we think there should be possibility that there are actually binary supermassive black hole, meaning that one star which is as massive as billion times solar masses might go around another similarly massive objects. And this is wonderful phenomenon, actually very energetic phenomenon, because these are also sources of gravitational waves. Because one of what I would like to show you, one of the actually simulations of these uh, was produced by NASA. These simulations. So this is the simulation produced by NASA, uh, which conceives two binary supermassive black hole going around each other. Uh, so as you can see, after time, it becomes very interesting, and actually, this the all the general relativity wonderful effects of the exotic effects of the general relativity kick in and becomes very very uh, violent systems. So the first blazar, which is actually thought of to be a binary supermassive black hole system, is known as OJ287. So in this picture, what you see is a accretion. This is a central black hole systems, something like 18 billion solar masses, and this is a primary black hole. So around which a secondary black hole, which is slightly smaller black hole, but still 150 million solar masses, goes round in a very elliptical orbit, and in due course what it does is penetrates through its accretion disk that extends up to kiloparsecs, and when as it penetrates punched into the accretion disk, it produces a sort of large optical flares. And to the right, you can see that. So every 12 years, or around 12 years, you can see a large. So astronomers were tracking this source past 100 years. You can see that it 900, 920, 1940, and 1960, all up to 2000. So astronomers were tracking these sources for about more than a century, and then you see that about every 12-hour year. I'm sorry. So we can see the optical flares. There's a flux, going right, flaring events every 12 years. So, so, so people think this is the indication. This is a strong indication of the binary black hole systems where this kind of scenario takes place. So we also study this source using our own data. Actually, the data from our optical using our optical telescopes. The data was taken from 2007 to 2016, nearly a decade long observations, and you can see the fluctuations, the periodic or quasi-periodic, something called quasi-periodic oscillations in the optical light curve, and these are indications of probably something in the jets or in the supermassive black hole systems. And there was extremely interesting phenomenon, and which we published in 2016 along with my colleagues all over the world. And similarly, in 2017, I reported a similar event. This was using 15 gigahertz telescopes in USA. So it was been monitored for many years, and in this paper I showed that actually we see this kind of oscillations, and this could be indications of supermassive black holes, and this work was published back in 2017. And similarly, this is another source blazar called J1043 plus 2408. Actually, the names of these blazars are according to their positions. The first is the right ascension, and the other, the plus 24, is a declination. So in this radial light curve, you can see that is about a 560-day quasi-periodic oscillations. So this indicates the supermassive binary supermassive black holes could be there. These are the observational indications. And later in 2019, so using NASA Fermi telescopes, I showed that actually there's another famous blazar, MRK 501. There are actually also not. So we found oscillations in optical telescopes, optical observations, and we found oscillations in radio telescope or radio flux. Now we also see in gamma ray oscillations or gamma ray flux, and which is very interesting result, and which I reported back in 2008, and it was covered in the international media as a big one of the big, well, big reporting. I mean, not quite a discovery, but still significant. And similarly, with my colleague, Nepali colleague Neeraj Desal, who came here from Michigan Tech to here. He was working here as a postdoc, and we studied several. Now, this was one source. The previous one was one source, but we analyzed many sources, 20 sources actually, and looking for this kind of signals. And we actually happened to found in a couple of sources similar signals, and this was published in back in this year. Actually, this was published in paper. So this tells the prospect of supermassive black hole in the systems, and this helps establish these indications. So I think now I would like to summarize my talk here. So blazars are one of the most luminous source, which is a relativistic jets, and these jets are powered towards the line of sight towards Earth, and these are supermassive black hole systems where all the effects of the general relativity, exotic effects of general relativity can be materialized. And we conducted a number of multi-frequency studies of the blazars using space telescopes, space and ground-based telescopes. And similarly, we detect quasi-periodic oscillations, or the modulation, a periodic modulation in the flux of the multi-frequency light curves of many sources, and which can indicate the binary black hole systems scenarios. And if they are, we can further confirm the binary black hole systems, then this will be dominant sources for the low frequency gravitational wave, and which can be detected by the future gravitational wave detectors, such as ELISA, which is similar to the space instrument, which is probably will be launched in 2030 years sometimes. So I would like to thank you for your attention.
Thank you, Gopal sir, for your nice presentation, and we are really happy that we saw, you have done so many works and close related to the topics which were related to this year's Nobel Prize. And now I would like to ask participants to raise your question if you have any. You can post in chat box, or you can just simply unmute your microphone and raise your question.
Yes, sir, can I ask a question?
Sure, go ahead, please.
Okay. It's very nice talk, Gopal sir. Thank you so much. I'm not doing research in astrophysics, but I'm teaching astrophysics in my university. So this is
That's
very,
great.
very useful for me and very interesting. Thank you for the talk. I have a quick question. So how are these blazars different from quasars, or they are similar, or I am missing something in here to understand blazars better? Thank you.
Uh, thank you for your question. Actually, it's a good question. So I think, as I mentioned earlier, so as a in terms of history, so people found some powerful radio sources, and but in the beginning they didn't see anything in optical. Later they found they were just a tiny stars, and because it looked like stars, and they were at that time called quasi stellar objects, and which was shortened later for quasars, and which later were found out to be supermassive black hole systems, and then they were grouped under a larger class, AGN, active galactic nuclei. So quasar is one of the class of a larger class. Active galactic nuclei is a quasar, and these quasar, some of them have jets, and some of the radio jets, very powerful jets. And if that jets happen to be point out towards the line of sight, Then from special relativity, if some light directly runs towards Earth with a special with a speed closer to the speed of light, then special relativity takes over. So it becomes very bright. It becomes the time. There's a time dilations and things like that. There's wonderful the effects of these special relativity kick in. So that's how they become blazar. Or that's how. So in short, quasar are larger classes than blazars. Quasar are a class of larger class Asian active galaxy nuclei, and blazar is a class of a subclass of quasar. I think I answer your question. Does that answer your question?
Yes, thank you so much. Thank you.
Hi, can I ask a question?
Sure, please go ahead.
That's very nice talk, Gopal sir. I have just one question that some scientists say that the jet that you just talked because of the AGI, active galactic nuclei, some scientists say that this might be because a galaxy is interacting with the neighboring galaxy. Do you want to comment anything on that one?
Yes, sure. So the jets formation. This is very interesting. I think you raised a very interesting question. The thing is that so like many stars live in binary systems, so there's a possibility that this kind of galaxies also live in clusters, and some happen to be very close, so that we can call them interacting galaxies. I showed you. I think earlier I showed you one of the such nearby. So they might be. So they're in kind of interacting galaxies, and so what happens in this case, as you can see, that because of the tidal effects, they're gravitationally interacting. Then many effects. It can induce many effects into the primary of or the secondary black hole system, or Asian or quasar. Actually, the Asian is galaxies, active nuclei. Nuclei is kind of galaxy actually. So and that produces this kind of effects, and this can induce instabilities in the accretion disks, in the trajectory, so that can lead to the formation of relativity jets. And you're right, there could be a significant contribution to the neighboring interacting galactic to the formation of jets. Very interesting question. Thank you.
I see one question in chat box. Someone is asking how to connect this talk with Nobel Prize talk. What are the differences? How close?
Okay. So black holes and supermassive black hole. So as I mentioned to you, black holes were a kind of subject of they were conceived long ago, but people believe. So as I mentioned to you, Einstein himself did not believe that black holes should exist. This is important that, and this is quite closely related to the discovery of quasars, which was mainly 50s, 60s in radio, with the development of the radio telescopes, and people were thinking. And then once again, I would like to go back to a little bit of history. So they were producing immense uh, radiation output of energy in radio, but we could not see anything in optical. But when we saw an optical, it was star-like. It's like just another ordinary star. But only when we analyzed the spectra, it appeared that no, it's not a star. It's a very, very far away. So now the question was, something which looks like a star, meaning in galactic range, within our galaxy, how, if that is very, very far away, how that you can imagine how powerful and how big that must be. Something very, very far away, yet it looks as at bright as the stars in our galaxy. And they were thinking, when they calculated the mass and energy, the 10 to the power 40 ergs per cm square. That's the number. And then when calculated it, the mass, and because of they were highly variable, so they were very compact. When we calculated the mass, it turned out to be from million to billion. So people, it left them astounding. The scientists, the astrophysical physicists. How is it possible, actually, something that can be as compact as billion solar mass, and which is within the area or region of compared to solar system, so which is compact within the area of, or the size of solar system. How is it possible? So there comes from that comes the idea of supermassive black hole. Observationally became more sound, and that promoted the physicists or theoretical physicists to look for more robust, rigorous proof for these black holes, or space-time singularity, the approach. And you realize that actually Sir Penrose, it was work at that time in 60s and 70s, and that was largely influenced by the discoveries of quasars. So to answer your question, these are supermassive black hole systems, and what in observations we are saying is the after effects, what kind of dynamics it produces, the supermassive. So they are very closely linked, and very directly related to the Nobel Prize, and yes, that's very closely related to the Nobel Prize.
Thank you. We have another question from Ashok Timsina. Sorry. What is the distribution of jet? Is it isotropic in both direction, or is it anisotropic in nature?
It's a bipolar jets coming from two opposite directions. It actually follows the angular momentum of the galaxy or the host galaxy. That's how it mainly starts, and is highly, and is in that sense highly isotropic, not isotropic, anisotropic. So again, because of this come with relativistic speeds, they are again very confined into a small angle. Actually, the angle is very small, and probably also by the magnetic field, because the magnetic field at the accretion is disk plays a huge role in launching or ejecting this kind of jets. So the answer is these are bipolar jets and highly anisotropic.
Yes,
I
go ahead.
have one question that came privately. I think it's to the host, so maybe I can recite that one. It's the question from Sir Home Cornell, sir. Hello, everyone. This is Home Cornell from University of Wisconsin. Gopalji, that was very informative talk on black hole. One thing that caught my eye was on your paper with so many co-authors, which seems to be common in nuclear physics, particle physics area. I have seen some paper with almost thousands of co-authors. Could you describe why they have so many co-authors? Yeah, that's the question that came from Home Colonel, sir.
Yeah, okay. I think he must be in different fields. Now the thing is that you can talk about. I can start with the gravitational wave, detection of gravitational wave. So one person cannot detect, in earlier times, like in movies, you must have heard about the Frankenstein. So the picture was that the lab would be in basement. There would be a lab, and a single scientist would work in, and he would produce result discovery. So that's no longer true in case of astronomy, astrophysics. So if you talk about the gravitational waves, there are many countries involved. There's a money, there's a grant, and there are many nations and government and then policies involved, and it's and further than the detection, is highly complex. There are theorists working on, there are engineers, there are instrumentalists, there are programmers. There are so many people involved. You might have heard about the black hole shadow. There was a young woman, I forgot her name. Can anyone, do you remember the name of the young woman who was presenting, who was doing most of the computer work? Anyone? So she says in her talk that she didn't know. Was that?
Katie Max, he's now
Yeah,
professor
yeah.
in Caltech.
Right. So she in that famous talk, she tells that she didn't know what black hole was. So that tells that she was only working on the code part. How to It was a interferometer, and the question was how to correlate them together to make a complex. The answer is there are many people. It's one people cannot do anything because it's observational astrophysics, and there are so many people involved, and there's a team, there's a group, they're multination. So most of this kind of for frontier works requires a lot of money. So that's why there are many co-authors. And as a policy requires, everyone who contributes has to be co-author. So there are co-authors. I hope this is
Sorry,
clear.
correction. Katie Bowman. Okay, Katie Mack is
Yeah,
astrophysics. Sorry, I missed that.
that's fine. I forgot her name. Yeah,
Anyway, thank you.
yeah.
Thank you. We have another question in chat box. Somebody's asking like, what are different types of black holes, supermassive and others?
To categorize these black holes, they were basically stellar and supermassive. But recently, so for a long time, we did not find intermediate size, meaning there are black holes size of 5, 10, 20, 30, like 100 within hundreds, stellar size black holes. And there are then supermassive black holes which is mass million times to billion times. Now, for a long time, we didn't find the intermediate class of black hole, but a couple of months ago there was paper claiming 1,000 times or something like that. So that's intermediate, but that's probably one paper. So up to now, stellar sized black hole and supermassive black hole, there are only two classes of black hole, and there's still a large debate why we can't find black holes that has a mass about 1,000, something in between 100 and million. So basically two classes.
Okay, thank you. We have another question from Saroj Pandey. He's asking, do these jets provide any information about the physics inside black holes? Is there any possibility of existence of the universe inside supermassive black holes?
Regarding what information they provide, they provide lots of information about this. Actually, these are the most exotic phenomenon in the universe. The formation of jets, not only jets, but jets are ubiquitous, actually found everywhere, and in proto-stellar system, star system, and anywhere. Even the comets, they're also kind of jets. The tail. But these are relativistic jets powered by supermassive black holes. So they provide the gamma ray that I showed you earlier. This probably is coming from the jets. So this is a signal. This is the light coming from jets. So they provide a wealth of information about the system where it's originating. To the second part of your question, if there could be universe inside the supermassive black hole. So up to now, people think that this is event horizon, and whatever falls into the black hole, the information is lost. We have no way to figure out what goes inside the black hole. Once it goes into, then it's lost. It's basically disconnected from our universe. It can have, there could be anything. Something, including Penrose, think that it's infinitely curved inside the event horizon, but it's detached from our universe. But there's a quantum information theory that says that So according to the current scenario, whatever falls into black hole, that is then out of causality. I mean, that's out of our this disconnected from our universe. So in that sense, the information is lost from us. But then, according to the quantum theory, information is never lost. So in some way, there must be a way to figure out what's inside them, and this is the active field of research. But as up to now, what goes inside, what falls inside, then we have no way of knowing what is inside the black hole, and there could be another universe. I mean, who knows?
I have a question. So, may I ask you a question?
Sure, please.
So, if I just look at the data and I think of the past Fourier transform, for example, over here, the frequency seems to be not so uniform in this case. If I just glance at the data, and I see that around 2015, 2016, there are some anomalies happening there. So, how do you decide that periodic oscillation just based upon the data?
Yeah, sure. Well, these are not meant to be strictly periodic in the first place because it's a whole complex system. Again, as someone pointed out, the interacting galactic, the another nearby galaxy must be interacting and disturbing and creating perturbations. So we cannot expect it to be strictly periodic. If we do the Fourier transform, you will not get a sharp peak at a frequency. That's why the name is quasi-periodic oscillations instead of periodic oscillations, or you can't see the sinusoidal waves. Again, because there's a black hole, there's a accretion disk, there's a magnetic field, and the accompanying electric field and relativistic effects. So this thing come into play and produce this variability, kind of variability pattern. But then we have something called red noise. This variability pattern are similar to something called red noise. Red noise is not noise, but if you do the Fourier transform, you see a power law, meaning you see variability in all time scales, from days to the decades. So that's a so in this kind of work, what we do is we test the peak, the Fourier peak, against the red noise to estimate the significance. That's how we figure out that if it's significant enough, then we say that yes, it's quasi periodic, not quite periodic. Again, we cannot expect it to be like strictly sinusoidal wave, but it's not periodic, but it's quasi periodic, indicating there is something periodic things happening in the dynamics of black hole.
Thank you.
I have another question from Vishnu Pandey. He's asking, how long people take data for one publication?
Well, it depends upon what kind of publications you want to make. These are space telescopes. The data is, you can do two things. There are archive data, which has already been there. One thing. The other thing is you can propose the telescope. You can submit a proposal and request them to observe something. But it all depends upon what kind of science you want to do with these telescopes, and you can do so many things with even with supermassive black holes, galaxies, jets, and depends upon what you want to do. So you just can't say exactly the data has to be this long or that long.
Yeah. Does anyone have any question?
CR sir, can I ask one last question?
Sure.
One very interesting thing, like there are two types of black holes, stellar black holes after the death of star, in supermassive black holes. That's what you mentioned. But it looks like that those supermassive black holes are also forming ultimately from the stellar merging of stars, right? So basically there is only one parameter which distinguishes one kind of stars from one kind of black holes from other kinds of black holes. That is the mass of the black holes itself. Is that right?
Right, that's correct. I mean, in black holes, mass is the only. I mean, a black hole has basically three, nothing but, you might have heard about no hair theorem. Black hole doesn't have hair, meaning it have mainly three properties: mass, spin, angular momentum, and a small bit of a charge. So basically, you can say a mass and angular momentum. These are the only main features a black hole has. But you're right, it's only mass. So stellar black hole forms due to the death of star, and more the supermassive black hole probably possibly by the merging of galaxies. But the question is that you can see these things at high redshifts, meaning very early universe. Now, this is a debate. This is a question that baffles some of the scientists. Is that you can see even this is as a high redshift quasars at the redshift of 11. I think the recent is 11, meaning very early universe. Uh, but for to merge galaxies, it takes some time. So now the question is how within that short period after the Big Bang, they were able to quickly merge and able to produce to supermassive black holes. So this is the question. But yeah, most of us thinks that it has to be due to merging. But now the question would be, what what about these early quasars or the early blazars that we see at high redshift? The time scale doesn't seem to be enough after the Big Bang. But you're right; it's basically mass.
Thank you.
So, may I one more?
Sure, please go ahead.
Thank you. One of the parameters that is, that was debated hotly was the cosmological constant. Can we use black holes to better understand cosmological constant, its values, or put some bound on it?
Well, I think this is one of my work in Nepal, and it certainly is. So, in terms of theories, in general relativity, you can have many different kinds of metric, meaning what involves in curbing which factors play the distortion of the space and time. So the cosmological constant acts opposite to the gravity, meaning the black hole produces a deep potential well, but the cosmological constant would rather flatten rather than to deepen the potential, the gravitational potential. But the cosmological constant should be the unavoidable part of the modern general relativity. It should be there in the form of dark energy, as we know, and it will definitely surely help to understand the dynamics if we include the cosmological constant. But the only problem we are having is that this seems to be very very small. Uh, so in black in so I and with Navinji were studying this stellar black hole systems at that time, including this cosmological effect. And in the stellar system, it barely has any effect, and it doesn't have any effect in the stellar systems. In supermassive black holes, yeah, it surely may have some effects, and it will be a very useful probe to this kind of black hole systems. You're right. This is a very interesting question.
Yeah. Any more questions? So I don't see any questions now. I have not related to the talk, but related to Nobel Prize. we see like there are two back-to-back Nobel Prize in astrophysics. Does it showing something like there are good things going on like astrophysics field that have more impact on human life? Because basically, I think everybody will accept that more uh, you know the fields which have more effect on human life are others, right? Because people want to use something. So do you have any comment about that?
Yeah, sure. This kind of question is not new. You can take it to another level. Like the world is has lots of problems, poverties, and things like that. Why do you want to study so much money in space telescopes and billions of dollars in this kind of? But one thing you have to understand is explorations and discoveries and research is quite linked to our existence. You know that anytime it's possible that one of the smaller asteroid will hit our Earth, and the whole human race will come to an end. It's possible. So we need to guard on the sky. We should be looking for things. So with this comes research, and besides our fascination of the mind, we're curious creatures. We're never satisfied with anything. This is built in our nature. Again, I emphasize it's also linked to our survival. So this is so the Nobel Prize you talk about, so that tells the fascination of humankind towards the understanding of the universe, mainly to the space time. So it looks like the space time we live in. It looks so ordinary, nothing interesting. Is so much interesting all of a sudden. Some of the black holes and curved space time. So if you talk about these other useful things, you know that all the technology, the internet and telephones and this kind of thing, the radio communication and this kind of thing, came with the with science. Uh, the telephones or the internet. How it was intranet in NASA, and later expanded in the form of the internet. So with inventions, with curiosity, with explorations, with research comes so many things. So it's always useful. So the term useful may not be looked upon as a direct, like something you can use it immediately, but it has a larger and deeper impact upon the whole human civilization.
Yeah, thank you. Well, I see another question from Parmanand Joshi. He is saying, very simple question. How do you recognize two equally bright stars that one of them is nearer than the other?
Okay. So you can tell if you just look at two stars in optical telescope and you see a similar brightness, you can see. Again, this is very interesting, also related to the discovery of quasars. But if you look at the spectra, you know, if they have same spectra, I think most of us know what is Doppler effect. So what happens is if something looking at so we can tell by the frequency change if something is moving fast away from us, or if something is coming very fast towards us, the apparent frequency changes, and this is the key to the understanding of how far or something is. Just by looking at the flux, you cannot tell if it's just look same size, but you have to analyze the spectra. So in case of the quasar, the astronomers were astounded. I mean, they were baffled by looking at the spectra. It nothing looked like the familiar spectra developed by the elements of periodic table. So later they realized that actually the hydrogen lines were shifted. So meaning red shifted, meaning something is going very fast away from us. And this was actually part of expanding universe. And from there, redshift, they found out that the star, the stellar-like object, which was quasi-stellar object, which looked like a star, actually is not a star. It's very very far away. So that's how we figure out the distance. But in short, just by looking flux, you cannot tell which one is far away, which one is not. But you have to looking at spectra, then you have way to figure out which one is farther and which is near.
Thank you. We have another question from Raghunath Pakurel. He's saying, nice talk. How does study of black holes help economy?
Well, these are indirect methods, very indirect. For example, maybe this gives employment to people for like us. you know, I don't know what I would do without this kind of research. What I would do, I don't know. I don't know anything, nothing more than this kind of research. But yeah, there's no direct economy, but indirectly there. When there's activity of science, there's a computer, there are softwares, there are people, there are travels and tourism. There's so many linked with it. Um, so it's activity in science. Actually, if you not black hole, but technology has always upper hand. You can think why England was colonial, because they had weapons. So far-fetched research is, let's not name as black hole, but far-fetched research is the key to development and prosperity. That's the important thing.
Yeah, thank you. Yes, I see somebody has posted a link. Benefits to the nation from astronomy and astrophysics. Yeah, that would be nice to talk. Whoever has that kind of curiosity. Yes. Now, does anyone have any question?
I have a quick comment.
Sure.
So once upon a time, Stephen Hawking was visiting Japan, and he used to talk about Big Bang and Big Crunch, and I think it's his one of his story that he said something like there were officials who told Stephen Hawking to not talk about Big Crunch because they were afraid that the stock market might crash tomorrow.
That's interesting.
So
Yeah.
looks we don't have any more questions. Coach Chandra, could you please stop recording so we can continue our informal talk,